All right, so let's get going with today's class. So I'd like to welcome everybody back from that extended 2-week spring break. Welcome you to this new experience for a lot of you, this online learning experience. So as we move forward, just a few words before we actually begin today. So this is going to be the new way of delivering the lectures. We're going to be doing it through my YouTube channel. If you have any questions about anything that is occurring, if you have any questions about the material that is covered, please check the announcements for how to attend my online office hours. They are now being done through Zoom, and the link is there for both the 1:30 and 4 p.m. office hour. And as we go through this, just to be fully transparent, we are going to have to do a little bit of catch up for the week that we missed. I am adjusting the deadlines. I am going to give you time to do all the things that you need to do. We are going to take the exams completely online, so they are going to be turned into take-home exams. So there's going to be a lot of adjustment. There's going to be a lot of changes, and there's going to be a lot of effort on both our parts to make this work. But I am confident that we can do it. I'm actually confident that we're probably going to learn some new skills and some new ways of interacting and learning from all of this. So I'm very hopeful. I'm going to take this as an opportunity to try out some new things and some new approaches. But with that being said, let's begin on Chapter 6, Hypothesis Test with Means of Samples, aka Day 1 of our face-to-face shutdown. So it's been a while since we've been together. It's been a while since we've seen this slide. So just to reiterate, it's always good to stay focused on our end goal. It's always good to stay focused on what is it that we are trying to accomplish here. And what it is we are trying to make psychology as powerful as that can be. We are trying to open up psychology to the world. So without the skills that we are developing right now, today, in Chapter 6, if we did an intervention, if we did an experiment, if we developed a new theory for 12 individuals with autism, and we found a new way of educating these individuals, and it was successful for these 12 individuals, without the skills we're developing right now, that's where it stops. And psychology would be a very limited science. It would be only for a very select elite few to benefit from without statistics. With statistics, however, we can open it up to the world. We can open it up to everyone. We can make the impact of psychology worldwide and affect a population, not just a sample. And that's what we're really going to be focusing on today. That final piece of the puzzle about how do we go from the sample to that population so we can make intelligent generalizations about what it is that we find, the discoveries that we make in psychology. All of this is building to what we're going to be starting next class, which is going to be 100% realistic, real-world applications of hypothesis testing. So no more assumptions, no more working with situations that are designed specifically for educational purposes. We are going to be getting into the real world, real techniques that statisticians use. So the ninjas of psychology, the ones that can get the results and get things done, the ones that can do all the cool things where we're analyzing the data, analyzing the treatments, making real discoveries about how to help people. Those are the skills we are now going to be doing and learning the real skills, the actual skills, the actual real life skills that professional psychologists use. So to keep that ninja metaphor going, right now you have almost all of the pieces of our five-step hypothesis testing program, and you almost have all of them. And what we want to do is we want to get you to the point where you have the complete set, where you are going to be ready, not just to follow along, not just to understand what's going on, but you're going to be ready to actually do this alone. And right now, out of our 5 steps in our hypothesis testing procedure, you have 4 out of the 5. Right as of this moment, you have 4 out of the 5 steps. You can do step 1. You can make a null in a research hypothesis for every single situation. You can do it for a two-tailed hypothesis test. You can do it for a one-tailed increasing hypothesis test. You can do it for a one-tailed decreasing hypothesis test. You have step 3. You can look up the lines in the sand. You can look up those critical values, and you can do that for a two-tailed hypothesis test, and you can do it for a one-tailed increasing hypothesis test and a one-tailed decreasing hypothesis test. Step 4, you can calculate your sample score on the comparison distribution. Step 5, you can conclude comparing step 3 and step 4. You can make the conclusion as to whether you accept the null hypothesis or you reject the null hypothesis. So those 4 steps we have, those 4 steps you can already do. The only one that's missing right now is step 2. The only one that is limiting your ability to do this in the real world is finding that comparison distribution, figuring out the characteristics of the comparison distribution, and that is the only missing step, and that is the step that we are going to do today. So you will have a fully realized, fully functional set of hypothesis testing skills, be able to do all the steps, and be able to do real psychology statistical work in the real world. So that's what's on our schedule for today. What we're going to do is we are going to relook and revisit samples and populations. We're going to relook at the distribution of sample means, because that is your comparison distribution. That vitally important concept of a distribution made up of the means of every single possible sample, that is your comparison distribution, because you compare your sample in an experiment or your sample of a treatment to that distribution of sample means. And the big part of today is going to be calculating or determining the characteristics of that distribution of sample means. We're going to use the central limit theorem for this. And then we're not going to have in-class practice. We're going to do that a little bit differently, but you are going to have access to the Excel sheets. And what we're going to do now for in-class practice is these will be more take-home assignments. So practice them at home, practice them after viewing the lecture. And then if you need assistance on them, you will join me in one of my online office hours. So the in-class practice, you're still practicing. I am still available to help you with the in-class practice, but it is going to be during the office hour times and not actually during the in-class times. And again, this is just one of the challenges that we are going to face together as we go through this shutdown period. All right, so let's get going on our hypothesis testing procedure. So we talked about the 5 steps of the hypothesis testing procedure. We talked about how you knew step 1, 3, 4, and 5. You could do those fully. You have the full realized set of skills for that. So now what we're going to take a look at is how do you do step 2? Because up until now, I've always told you we're going to see how to do this next chapter. And now, for now it has to be given to you. And then I would give you the characteristics of that comparison distribution. I would tell you the mean, and I would tell you the standard deviation of the comparison distribution. That was in the past. That's what we've done up to this point. Right now, today, is where you actually see how to do it. Right now is where we actually learn how to calculate those 2 characteristics, the mean and the standard deviation. Now, it all ties back to samples and populations. And it all ties back to that idea that we are dealing with samples. We're only ever having access to samples, and we use those to estimate what we're really interested in, which is the population. So we use a sample mean to predict a population mean. That's what we do when we gather data. However, if you're dealing with an unknown population and you take a sample from that population, you start grabbing individuals from that population and you start measuring the individuals from that population, you get your sample from that population. Because the population is unknown, you can measure that sample, you can measure the sample mean, you can measure the sample standard deviation. But the one thing that you cannot know is where did your subjects come from in that population distribution. We have no idea where these subjects were located in that distribution. So did they come from the center of the distribution, such as this sample, which led to this particular sample mean? Or did they come from an extreme end of the distribution, an extreme low end? which would lead to a very different sample mean, a very different average score per subject. And then the other possibility is that they came from a very high extreme of the population. And once again, we do not know whether this is the sample that we have access to, and we do not know whether it's a previous sample that we have access to. We don't know where our subjects came from that are in our sample. So that's our challenge, but we use this in statistics. We take this challenge and we use it, turn it into a strength, and we turn it into this idea of a distribution of sample means. So the distribution of sample means, this is actually the entire collection of all of the samples from a population that can be done or made with a particular size of a sample. So in our example here, we were taking samples of 5 from the population. We were taking a look at 5 individuals each time from a population. If we did a distribution of sample means, it would consist of every single possible collection or sample combination of 5 individuals from that population. And we would measure all of the means for every single combination of 5 individuals from this population. And those means would form their own distribution. And that distribution of sample means is the distribution of sample means. And we've introduced this idea a number of times so far because it is a little bit, it's got a lot of moving parts. So give yourself a little bit of time, you know, if you still haven't, if it still hasn't sunk in, you know, go through these examples a few more times. Try to keep everything distinct because there are a lot of moving parts. We're dealing with 3 different ideas: the population distribution, a sample on its own, and then a distribution of a bunch of samples. So once again, the very kind of simplistic example that we used is the distribution of sample means for dice rolls. So the population of dice rolls, if you take a look at every single 6-sided dice roll for a fair 6-sided dice that has occurred in the history of the universe, that's the population distribution right there on the right. That is the outcomes. It's a flat distribution. Those are all the 6-sided dice rolls that have ever occurred. You can see that they have an equal frequency for the outcomes. That means that your 6-sided dice is fair. So in this case, if we took a sample from that population, and it was a sample of a single dice roll, it was like a case study of a dice roll, we would find that sometimes the dice roll would have a mean of 5. For example, if you roll a 5 on one dice, that's a mean of 5. If you roll a 4, that's a mean of 4. If you roll a 1, that's a mean of 1. And if we took every single possible dice roll and we calculated the means, we would get 6 different means. There's 6 possible dice rolls. We would get a mean of 1, a mean of 2, a mean of 3, 4, 5, and 6. And if we took those, if we took the average of those means, if we took the mean of those means, then we would end up with a mean of 3.5. So the average sample mean is 3.5, and that is exactly the same as the population mean. And that is one of the principles of the distribution of sample means. So if we take a look at the distribution of sample means here, you'll notice first off that the average, the center point for this distribution of sample means is 3.5, the very same center point as the population distribution. The second thing that you'll notice is that the distribution of sample means for a sample size of 1 is the same shape as the population distribution. So those two things are part of what we're going to see today in the central limit theorem. And that sometimes gets a little bit confusing because in the case of a single sample, a sample size of 1, in the case of a sample size of 1, your distribution of sample means from that population is going to be the same as your population distribution, because your population distribution is a distribution of individuals. And when you have a single subject as a sample, your distribution of sample means is also a distribution of individuals. It's the same distribution. But weird and wonderful things happen when you add a second subject. So when you add a second subject, when you are now rolling 2 dice, when you have 2 subjects in your sample, and you do every single possible combination of 2 subjects from your population, what you get is you get a very different distribution of sample means. All of a sudden, your distribution of sample means starts to look different than your population distribution. All of a sudden, it starts to take on its own shape. And as you add subjects, that distribution of sample means continues to change. And as you add even more subjects, it continues to change. The population distribution is not changing whatsoever, but the samples that you get from that population, their distribution is changing. And the weird and wonderful thing about this is that as you keep going, that distribution of sample means, aka a sampling distribution, that distribution of sample means begins to take a very familiar shape. It starts to look like that normal curve. So this is one of the reasons why we take samples, so that we can force that distribution of sample means into a normal curve. We want to force it into that shape because that's a shape that we know. That's a shape that we understand how to work with. That's the shape that makes psychology possible. Now that shape, you can determine it in a couple of different ways. One way that you can determine it is by taking every single sample from a population. So I can use Excel to calculate every single possible sample of 5 dice rolls, from the population of dice rolls. And that's how I generated these graphs. However, in real life, in the real world, you can't just keep rolling dice, right? You can't just keep rolling human subjects when you're dealing with psychology. So in this case, we have to have a solution where we only have one sample. You take one sample from the population, and that's what you get to work with. That's what you get to deal with. So the question then is, how do we figure out this distribution of sample means? How do we figure out this comparison distribution that we need, absolutely need, for hypothesis testing, because it is step 2. And that's what we're going to turn to today. So determining the characteristics of the distribution of sample means, getting that mean of your distribution of sample means, getting the standard deviation, the spread of your distribution of sample means, all of that comes from the central limit theorem. So for the central limit theorem, you don't have to understand why it works the way that it works. You don't have to understand what I like to call the mathemagic behind it. That's more grad level work. That's more specifically statistical work. All we need to know, however, is how to use it. So this is like a light switch, right? All we want to do is we want to fill the room with light. We don't have to know the electricity involved. We don't have to know the electrical theories involved and the wiring involved. All we need to know is that if we flick that switch, light goes on. We flick it down, light goes off. Same thing with the central limit theorem. So you're not gonna be able to look at it and say, oh, okay, I understand why it's the way that it is. But just know that it is the way that it is, and we need to understand that. We need to be able to use that for our purposes. So what the central limit theorem says is that for any population with a mean of mu and a standard deviation of sigma, so any population that has a mean and a standard deviation, when we take the distribution of when we calculate the distribution of sample means for a specific sample size of n, so maybe we're taking a sample size of 10, maybe we're taking a sample size of 20, maybe this is a huge study and we have a sample size of 1,000. However many people in our sample, it will have this distribution of sample means will have a mean of mu. So a mean equal to the population mean. And it'll have a standard deviation of sigma divided by the size of your sample. So it'll have a standard deviation that is related to the population standard deviation. Not the same, but related to it. And it's related by dividing it by the square root of the size of the sample. And the last piece that we get here is that this is going to approach a normal distribution as the size of your sample, that n value, that size of your sample approaches infinity. And for all intents and purposes, once you get past 30 subjects, regardless of your population distribution, you can assume that you're working with a normal distribution. So take a look at what we have and take a look and think about why this opens up psychology for everybody. First off, point number 1, it's for any population. It doesn't matter what population you're interested in. you can calculate the distribution of sample means for that population. So it doesn't matter how narrow your focus in psychology, it doesn't matter how new the group that you want to help out is, you can do psychology, you can do statistics to help that group. The distribution of sample means will have a mean of mu and a standard deviation of it'll have a mean the same as the population distribution and a standard deviation equal to the population standard deviation divided by the size of your square root of the size of your sample. That was a mouthful. Basically, that's the way we calculate the characteristics of the distribution. And then the last point, it approaches a normal distribution. That opens up the appendix that we can use. That means that we know the distribution. We know how to figure out portions of the distribution. We can do the psychological work. And that last point, we've seen it before. Here it is one more time. On the left side, if that's your population distribution, on the right side, that's your distribution of sample means for a sample size of 1. Same distribution, because on the left side we have individuals, on the right side we have individuals, right? On the left side we have a distribution of single individuals, on the right side we have a distribution of single individuals. But when we go to a sample size of 2, all of a sudden that distribution of sample means changes, because now on the left side we have a distribution of individuals, but now on the right side we have a distribution of couples. We have a distribution of 2 people. And now on the right side we have a distribution of 3 people. And now we have a distribution of 4 people. And now we have a distribution of 5 people. And notice with each additional person in that sample size, we are getting closer and closer to that normal distribution curve. We're getting closer and closer to that bell shape that we know how to work with. And if you're dealing with a differently distributed population, once again, sample size of 1 looks exactly the same. Your distribution of sample means looks exactly the same as your population distribution. This changes as soon as you go to a sample size of 2. Now we have a distribution of couples for the distribution of sample means. On the right side, those are scores from couples. Those are means from couples. And now we have means from groups of 3. And now we have means from groups of 4. And now we have means from groups of 5. And notice once again, closer and closer to that normal distribution shape, closer and closer to that bell curve that we know how to work with. And this works for any population distribution. So once again, sample size of 1 looks just like your population. This is a huge problem, because if you don't know what your population looks like, you're not going to know what your distribution of sample means looks like. If you don't know what your distribution of sample means looks like, you can't do psychology. You can't help the world. So what we do is we start taking samples of more than 1. So we take a sample size of 2. We take a sample size of 3. Sample size of 4. Sample size of 5. And you can see already we're starting to get that nice bell shape. We're starting to get that nice normal distribution. And this is what we're going to lean on. This is what we're going to use going forward, because as we're going to get more realistic, we're not going to know what the distribution of our population is. But we are going to know what the distribution of our sample means are. And specifically right now, we're going to focus on the fact that we're going to know the shape, because that shape, as you go from 1 individual in your sample to 2 individuals, to 3 individuals, to 4 individuals, all the way up to, well, to 5 individuals, all the way up to how many individuals you have, it starts to get, starts to be shaped like a normal curve. All right, so we've talked a lot about the central limit theorem right now. We've talked a lot about the distribution of sample means. Let's get down to business. How do we do this calculation? How do we actually get these numbers? So rule number 1, we're going to do this much like your textbook, just so that you can see the parallel structure there, just so that we are using the same terms. Textbook seems to go a little bit too complicated, so hopefully I'll be able to help you understand a little bit of what's going on there as well. So let's start with rule number 1. So rule number 1, the mean of your distribution of sample means is the same as the mean of a population of individuals. So they write this out as, on the left side, population M sub M. That is the mean of your distribution of sample means. So you'll notice that the symbol for mean is in there twice because it's the mean of a distribution of sample means. And what this is saying is that that equals your population mean. So the mean for your distribution of sample means, the capital M, equals your population mean, Greek letter mu. That is rule number one. So that is where we get the mean of our distribution of sample means. That's where we get the mean of our comparison distribution, the mean that we use in step 2. Rule 2A. So this is about the variance of the distribution of sample means, and we're not going to spend too much time on this because this is not the number that we actually use. We use standard deviation, but let's do it the way the textbook outlines it, just so again you can see that parallel structure. So the variance of your distribution of sample means is the same as the variance of the population of individuals divided by the number of individuals in each sample. So once again, on the left side, the variance of your distribution of sample means equals your population variance divided by capital N, which is the size of your sample. So to write it out in terms that we use, the left side there, the variance of your distribution of sample means, that variance sub M, variance of distribution of sample means, equals variance of your population divided by little n, the size of your sample. Now that's rule 2A. That's not the one that we're going to use the most often. The one we're going to use the most often is rule 2B, because that's the standard deviation. That's the number you use when you're calculating the z-score for your sample. That's the vital move that you need. And what the central limit theorem says is that your population standard deviation, your distribution of sample means standard deviation, the spread of your distribution of sample means equals the spread of your population divided by the square root of the size of your sample. So if you look back to the previous slide, if you look back to this slide right here, you'll notice that to get to rule 2B, all we're doing is taking the square root of everything. So we end up with, instead of standard deviation squared, we end up with standard deviation. Instead of the size of the sample, we end up with the square root of the size of the sample. And to put it in terms that we've seen, we have your standard deviation on the left side, your standard deviation of your distribution of sample means equals your standard deviation of your population divided by the square root of the size of your sample. And this standard deviation of your distribution of sample means is so important. Not only does it get its own symbol, but they've actually changed the name of it as well. They call this the standard error. So in your textbook, in your further readings in psychology, as you kind of go through your academic study of psychology and beyond into your professional career, you will see statisticians reporting that standard error over and over and over and over again. This is what they're reporting, the spread of your comparison distribution. So this gives you an idea of how important step 2B is, because that term, the one that we're going to use to calculate the comparison distribution, the one that we're going to use to calculate where our sample is in the comparison distribution when we calculate our sample z-score, that's the standard deviation that we use. That is called the standard error. It got its own name, and that should be a huge flag that says this is something that we really need to take notice of. All right, and then the last rule is that the shape of the distribution of sample means is going to be approximately normal if one of two conditions is met. The first one is that the sample size is 30 or more. So if you have a sample size of 30 or more, you can be pretty sure that your distribution of sample means is going to be a normal distribution regardless of what your population looks like. So that is criteria number one. If we have 30 or more, we will know for a fact that our distribution of sample means is normally distributed. The other criteria that could be met, so remember this is either or, either you have a sample size of 30 or more, or if you are already beginning with a distribution, a population distribution that is normal to begin with, like the distribution of IQ, the distribution of heights, the distribution of SAT scores, if your population distribution is already normal, then regardless of your sample size, your distribution of sample means will also be normally shaped. So these are the two conditions. Either or is good enough to make sure that we're dealing with a normally distributed distribution of sample means. That we get that bell curve, that means that we can open up the appendix and figure out what we are dealing with. All right, so that is the basics of what I wanted to cover for today. So what I'm going to mention now, we have in-class practice that you can do. Clearly, we're not in class right now. So what I would suggest that you do is I would highly suggest make sure that you are going through the hypothesis testing practice. So here's the hypothesis testing practice, and let's just zoom in to that selection. Whoops, you know what? Let's undo that because that actually made things smaller. All right, so once again, we have a hypothesis test that we've been doing before. So this is, once again, just practice so that you can get practice with using the comparison distribution. So make sure that go through this one more time and make sure that you are using the comparison distribution. So the first thing we have to do, the first habit we have to break that you got through the homework is using the population distribution. That is the biggest mistake you can make in chapter 6. Get into the habit of using the comparison distribution, specifically using the comparison distribution's standard deviation. So run through this hypothesis test one more time, and at the bottom here, it's got whether or not you got it yet, you got the answer yet, or whether or not you still have a little bit of work to do. But then the crucial part for this class today is to make sure that you can get this comparison distribution here. So it's not a lot of in-class practice. We just really need to focus on this one idea. So what I would like you to do is fill in from the information in the question, fill in the population distribution mean, fill in the population distribution standard deviation, and then calculate your comparison distribution, your distribution of sample means, calculate the mean of that, and then you have a step-by-step procedure here where it's asking you to put in the population standard deviation and the sample size. Take the population standard deviation divided by the square root of the sample size, and you will put that in your answer cell there. We do not have an updated grading scheme for that because the answer you're looking for is right there. So make sure that you find out how to get to that particular answer for your comparison distribution. That's what we're looking for in this practice sheet. All right, so that is going to be your at-home practice. Once again, give this a try. If you're struggling with it, if you have any questions, feel free to drop in on one of my office hours. No booking necessary. The links for the office hours, the links for the Zoom meetings are in the announcement, so make sure that you find those links. You might want to copy them somewhere so that you have them readily available because we are going to be doing that for our in-class practice moving forward. All right, so before we end, I'm going to reiterate this slide one more time. This is a very important slide. I highly recommend take a look at this slide, think on it until you're absolutely rock solid with the fact that we are now dealing with 3 different distributions. The first distribution we're dealing with is your population distribution, a distribution of individuals. The next distribution we're dealing with is your sample distribution. You take individuals from your population and take their scores, and those scores form their own distribution. And then if you take all the samples possible, they're all going to have means. And if you take those means, you can make a third distribution, which is your distribution of sample means. So we are going to be using these 3 distributions. Now, the last thing that I'll mention is that for those of you that hopefully, if you think critically about this, hopefully as you followed through the lecture notes, one item might have come to your mind, and that is the fact that we are using our knowledge of the population distribution in order to calculate the distribution of sample means. And as I mentioned before, we usually don't have access to that population distribution. So keep in, know that and take comfort in the fact that We are going to deal with that very, very soon, but this is just kind of the last little unrealistic aspect that we're including so that we can learn what this distribution of sample means is and how it's used. But we will address that issue as we move forward into more realistic hypothesis testing, and that's going to start next class. So just want to remind everybody about the 100% pretest points. So continue to work with your MyStatLab study plan. This is for the Chapter 6 pretest. So the due date on that pretest is going to be moved. So I am finalizing that to accommodate the shift in our weeks. I'm going to finalize that to accommodate the catch-up that we are going to have to do. So we are going to have some extra lectures per week in order to catch up to where we're supposed to be. But do know that we will be adjusting those due dates so that we can get a complete course and a complete education in for everybody in this class. So we're going to be doing that. And just to put it on your radar, homework assignment number 9, I'm going to be updating the homework assignments as soon as possible. But homework assignment number 9, this is now going to be due April 6th by midnight. So I will update those for you. I will update the syllabus. All of that is coming. We are scrambling a little bit to get all of this in and done. But just know that it is coming. We are going to take care of all of that business, and you will have time to accomplish all of these goals. And I am going to try my hardest to make sure that we have a full course experience, regardless of the fact that we're not doing this face-to-face anymore, regardless of the extra work that it's going to take from all of us to go online. I am dedicated and committed to a full course experience for everybody. So that's all coming. I ask for your patience just a little bit longer as I put the final touches on it, but just know that it is coming. You will have ample time to complete your work, and that's what we're going to try to do for the remainder of this semester. So that is it for week 12, class number 1, chapter 6, hypothesis test with means of samples. So let that sink in. Do the practice Excel sheet, try the pretest once it goes live, and then again, if you are having any difficulty with this, feel free, drop in to any of the office hours, simply with the Zoom app. If you don't know how to use that app yet, I highly suggest explore it. It is available through 1IU. It's available through the announcements. You can simply just click on a link and it'll take you to my Zoom meetings. So again, those are going to be Tuesdays and Thursdays, 1:30 to 2:30, and Tuesdays and Thursdays, 4 to 5 o'clock. So I will be there waiting in my online waiting room. Feel free to drop in. Other than that, thanks so much for joining me for this first in our online series of lectures and meetings. And again, we are in this together. We're going to try our best to make sure that we get a complete experience, and we will see you next time.